Good afternoon.
Good afternoon. Be a little bit here while we get situated, I think.
Of course.
And let me see, you guys are
UC Berkeley Star. Yeah.
Right.
What's the number?
Team 105.
105.
Are we getting all 60 of you on the Zoom call here?
Unfortunately not. We couldn't quite, not everybody could make it. There's like 10 of us, I believe, for here today.
Is that how many people you typically have working on something? Or like, to me, 60 people seems like a really large amount. So
yeah, of course. So we have a lot of diversification in terms of our projects. For Eric specifically, the core team was around 25 to 30 people, because we did have like payload specialists, and we had a stack of research projects in our payload, and each one had a team associated with that. Yeah, here, he's got it. Raji's holding it right now. That's our payload stack that we flew. So yeah, we have a lot of opportunity for micro projects within the IREC kind of total scheme.
Mm-hmm.
Yeah, let me. Okay, so let me kind of get this straight how this is going to work. We're showing you our video to start, right? And then there's the Q&A portion afterwards.
Actually, I believe we've all watched your video already, so we're prepared to ask at least a few questions of you. And yeah.
Okay, well, yeah, we can definitely get started. Feel free to hit us with what you got.
This is Mark. I had a question on your microbial fuel cell. I just had a student do a science fair project on that topic, and it was very interesting. I just wondered what got you started in that and what you learned from using that idea.
Yeah, I can speak a little bit to this. It's hard to see, but the microbial fuel cell is in fact here. It's full of dirt. The main catalyst for this, I would say, is the fact that we had a bioengineering student on our team who had some background in kind of this area and was interested in flying one of these. We pride ourselves, especially in the payload team, on recruiting sort of a wide variety of people from backgrounds like physics and, in this case, bioengineering. So we get a lot of interesting science payload ideas. There's nothing extremely particular about flying it on a rocket, but we thought it would be a neat idea, and it fits pretty well into the CubeSat form factor.
So as far as things you've learned from that payload, isn't it like enough to write a research paper on?
So we wish it were. We did fly this payload successfully. We gathered data during flight. It turns out that during our flight conditions, we did not observe any statistically significant difference in the data than if it were simply running on the ground. This was expected by payload engineers. So no research paper is coming out of this payload with likelihood, but it was certainly a fun project to work on.
No Nobel Prizes?
Sadly not.
Perhaps in the next iteration.
All right.
Video mentioned something about algae interrupting the anaerobic processes of the fuel cell. Do you know how that happened, or was there a investigation into what caused that?
Sorry, could you repeat the first part of the question?
Your video mentioned that there was some algae that interrupted the processes in the fuel cell. How did that occur? Did you discover that, or is it just something that happened? And
yeah, so this is in our development process. It wasn't kind of related to our final flight article, but we found, I guess, during the first iterations of constructing our fuel cells, that one of them got kind of contaminated. So that it's a pretty sensitive biological environment. And especially preparing the payload for flight was difficult because it's a fairly sensitive biologic thing, and if you have to cancel a flight or there's a delay or something, things can grow in it. and that's what ended up happening.
I was also curious about the active stabilization system. I want to know a little more about like you're using that to hopefully add stability to the rocket is what the purpose is, and then like how did you decide what moments you needed to induce, and how did you go about that, and other things like that?
Yeah, so the active stabilization payload is based on an open source project. So this isn't completely from the ground up, but so I'm not an expert on this, but my understanding of how it works is there's an IMU that senses where the payload stack is, and then there are these 3 servos, and at every time step you can calculate basically the difference in orientation between the platform that is to be stabilized and the payload stack itself, and you can do some inverse linear algebra, and you get a set of actuation outputs, 1 for each servo, and then that's applied at every time step as quickly as possible. So there's a limited frequency response to this, but we believe it works quite well in testing.
Oh, has it been flown, or is it just ground tested?
So it has been flown. It ground tests very well. We had a last-minute firmware issue in flight that impacted our ability to gather data about whether it worked very well or not. So we have some flight data, but in the future, I think we would look to flying this again with some firmware upgrades. All of our payload missions were considered non-mission critical, so we weren't going to cancel our launch in order to continue development. So we don't have crystal clear data on the success in flight. So it has been flown, and it survived the flight.
Ah, well, that's important. I have a broader general question now. So obviously we're not in the desert this week launching your rocket, but let's all imagine for a second that you were transporting your rocket out to the 105°F New Mexico desert, and you are following your procedures to assemble it. And what goes wrong, and what do you do about it?
So kind of the interesting thing here is at our launch, we were in the desert and 109-degree temperatures in the Mojave. So we can answer this with a pretty high level of precision. We did one final ground test and Julie can speak to this as our resident expert on recovery, but we did our ground test and there were some delays associated with that. And as we know, IRIC has this grading system based on the time to kind of full assembly and to time to the pad. So I think we definitely improve on that in our next launch. And if we were in New Mexico right now, it would be better, but that's still like a large source of delay for us and something that we're working on, definitely.
One of our big problems on the recovery side was that it got so hot outside that the scale that we were using to measure black powder masses fritzed out. We were in the middle of measuring, the screen just suddenly gets like very, very black. I think the battery might have gone negatively affected, and it stopped reporting. And we had half of our black powder measured out, and so I just told our recovery leads, like, we're gonna measure by volume instead of by mass, because we already had precisely measured out black powders already. So we just used that as kind of like the baseline. We were able to successfully get that, but that was probably the biggest thing, that the heat affected our technical stuff on my side.
And now let's imagine that you've made it to the launch pad and the rocket goes through a flight cycle. What failure modes do you think are most likely to happen to your flight, and what's the outcome?
So we can speak to a couple failure modes that were considered and mitigated. One thing, Jenny, do you want to speak about fin flutter and what we did there?
Sure. So we did fin flutter analysis, and we found that our fillets that we had as our primary design iteration were right on the boundary of where significant fin flutter would be experienced. So in order to mitigate that ahead of time, we applied fin-to-fin glassing. So that was done kind of with considerations of the pandemic, on a rooftop, kind of a few weeks out, just to ensure that no matter what, at flight, in kind of the edge case, we would not experience fin separation or fin flood.
Yeah, and aside from that, I think the majority of our remaining failure modes are recovery based. So those are mostly mitigated in design. I don't know if any of the recovery folks want to speak to at least one specific thing that we did.
All right, I'd say Julie and I would both be able to talk about why the ground test serves. Julie, if you want to kind of elaborate why we do the ground test, what the important things we do for the ground test. I know you and Hadar were working on like electrical connections, especially.
Yes, that's one reason for the ground test is just to verify that everything has been connected successfully, because if anything hasn't, we usually will notice it at that point and we have a chance to fix it before we get to the pad. Another thing we were verifying for the ground test was that our black powder charges were sufficient to separate the rocket. Yes, is there anything you want to add to that, Felipe?
Yeah, one of the things that one of the kind of like one of the changes that I remember we had to kind of adjust for was, I think Airframe had drilled some new holes for something they had needed. One of the Airframe members can obviously clarify what the need was. And so we had to make sure that we were adding in sufficiently more black powder so that, you know, that change in the necessary pressure for separation would work, but not so much black powder, obviously, that we're over exaggerating and overcorrecting for that. And so we needed to test that on the ground at the location to make sure that the conditions were as closely matched as possible.
And then, do you have something to add?
Oh, just like that was compensating for a new vent hole calculation we were applying.
I wanted to follow that up with, so considering that hopefully next year we'll be in the desert and launching this rocket, maybe it'll be you, maybe it'll be a follow-on team. How are you capturing what you did this year and any lessons you might learn so that the future teams can gain from your experience?
Of course. So we focus a lot as a team on new member education. We pride ourselves on being kind of an organization that can really bring anyone who has drive and an interest in rocketry and kind of going to the next level and getting an understanding from like near nothing, just some technical class background, all the way to being able to fly their own high power rockets. We kind of have an L1 certification program, and we try very hard to maintain documentation that is sufficient to kind of explain what our team has experienced in the past and to kind of build on those experiences for the near future. A lot of that is kind of ensuring that people have a very clear understanding of rocketry basics of high power. That's a new initiative that's been started this year and it's going to be expanded next year. And a lot of kind of the lessons learned, everything that we've done on this rocket, elaborating from our subscale Air Bears to Bear Force One, kind of has become our team based on it's been a big topic of discussion because this is kind of the first time we've participated in IREC, and we hope to keep this as our primary competition moving onwards.
Just to add on to that, specifically from our flight this year, we do have a post-launch assessment review. So we have a write-up of everything that happened, everything that was not nominal, and recommendations for the future prepared by everyone who went to launch.
That's very good. Mark or John, any questions?
Just general question about team participation. Did you all feel equally loaded in your work during the time, or did some feel more work than others?
So the unfortunate truth about this year was that kind of with coronavirus and university policy, there was no way to have kind of group participation, group builds in that kind of fostering that sense of community that we've had in past years. So a lot of work was done using kind of handoff and with no people kind of in contact at the same time in order to follow university procedure to the letter. So although there was a build team that worked on everything and the rocket was passed around, it was definitely a smaller group than it would have been had the pandemic not occurred. Yeah. People still definitely had a chance to participate virtually. And there was, again, that's where that 20-person figure comes from. Those isolated projects all came together in the end, right? But kind of the top-down view that we had where we would go out and kind of all look at the rocket, all work, and have that centralized approach, that wasn't available to us.
I can also say, as since we were doing some manufacturing prior to the pandemic in the early spring of last year, that at that point I definitely feel like our participation, at least in manufacturing, was being a lot more evenly spread. And like Jenny said, the pandemic really changed a lot of the things that we had to do.
And as a member that joined in the past year, and I did a lot of design work online, and I was able to utilize a lot of the resources that STAR has available, and that still allowed me to contribute to this project overall.
Yeah, I will say, even when people couldn't be hands-on manufacturing, and I have this payload stack sitting next to me, a lot of these parts were printed in my bedroom, but they were designed by people all across the country. So we would send each other files, and so some of the manufacturing became a single point of contact, but as far as the design work and working on the rocket in general, I think we did a pretty reasonable job of splitting things up, pandemic considered.
I have kind of a wrap-up question. Is there anything that you would like us to know about your project in particular that perhaps you haven't been able to adequately explain from our questions or through your report or the video you performed, that is just a particular thing about your project or team that we should know?
So this rocket, everything from Air Bears to Bear Force One to our final flight, it's been an enormous labor of love. Like it's been with us for 2 years now, from conception to flight, and it's been like an enormous effort across time zones and across kind of hundreds of miles to get it all working and integrated and into like the perfect final physical flight configuration that we flew. So I just wanted to kind of have that final element of, we did fly this rocket, we did get to an apogee of 10,128 feet at FAR 1030, and we did place first in that competition for our class. So yeah, that's kind of the final element I wanted to share.
Thanks. I know we've seen some UC teams at the Spaceport America Cup before, not you guys, but other. Is there an internal rivalry going on in the UC system to you different rocket groups get together?
So we're actually working on a collaboration. We have the same mentor. Our L3 mentor this year is the same as UC Santa Cruz's. So hopefully there's a kind of a more of a in-person collaboration next year with those folks, just because we have that connection to them. But yeah, I definitely hope that in the future that'll be a resource we can all kind of create a UC block for collaboration really soon.
All right. I think that's all from me. Anything else, Mark or John?
Yeah, you said you were launching out of Mojave. Was that at the Friends of Amateur Rocketry site? Or
Yes, at FAR.
Are they co-located with the Reaction Research Society?
Sorry?
Yeah,
Could you repeat that?
Are they co-located with the Reaction Research Society? RRS?
Yeah, RRS has a site directly next to the FAR site, but they're not the same site.
Yeah, I was out there eons ago, went to one of their 3-day motor making classes, so that's a nice site. It's a really good setup.
Yeah, no, actually that's part of our 60 team kind of initiative. We do have like a experimental solids group that's probably going to take that same exact course over the next few months.
That's cool. Yeah, I'm jealous. But no, that was good. Thank you very much for your presentation.
Thank you.
Thank you all.
Much appreciated.
Let's see, I think we need to